Welcome. In this video, we'll take a look at section 6.3. We're going to be working with trigonometric equations involving double angles and triple angles and other arrangements. So let's jump into our first example. We have a sine 2x is equal to negative 1 over the square root of 2. So one thing that we can consider doing right off the bat is just considering what negative 1 over square root of 2 is for us. This is another way we can write this. If we go to rationalize this, we'll probably come up with something that is a little bit more familiar to us in terms of our unit circle. If I go to rationalize negative 1 over the root of 2, we'll end up getting negative root 2 over 2. So this is a little bit more familiar side ratio for us. So we certainly can use this in our calculation. These are the same numbers as the original. Another thing that we might want to consider doing with these double angles and later in whatever triple angles or quadruple angles we have, we can consider just replacing this 2x by some other variable. And we could call it theta, we could call it y, whatever we want, as long as we remember that that's representing this 2x that's in the original problem. So here I'm going to call theta, this dummy variable, equal to 2x. And so this is going to be my new equation if I rewrite this. And it'll remember to have to go back to this by the end, but it'll make it a little bit easier for us to work with in the time being. So we can say that this is going to be sine of, we'll call this theta, equal to negative square root of 2 over 2. Well, hopefully taking a look at this looks a little bit more familiar to us, where the sine function is equal to negative square root of 2 over 2. This ratio here comes up in a few places for us, namely where the sine function is negative. So we would find this side ratio in the third and the fourth quadrant. If I consider negative square root of 2 over 2, this is really going to form a 45 degree or a pi over 4 as the reference angle. And so we can consider the angles that give us a reference angle of pi over 4 and pi over 4 in both the third and the fourth quadrant. Now let's consider what these angles are, and then we'll try to list out a few solutions here for theta specifically. So theta here, working around our unit circle, the first angle that we have here, and I'll start to color these, is going to be this angle right here. That would be the angle of 5 pi over 4. The next angle that we would have is this next one coming around our circle. This would be equivalent to 7 pi over 4. And so this would be good to stop here if we were just solving for our unoriginal variable within the range of 0 to 2 pi. So let's consider what all possible solutions would be here for our angle within 0 to 2 pi. It might be helpful, since we do have this 2x as our theta, we're really going to be dividing this theta value by 2 to get back to our original variable here of x. So it might be helpful to have a few more solutions for theta so that we can have a complete list of solutions for this x value. So what I'm going to do is I will find some coterminal angles to these original 2. So if I considered a coterminal angle to 5 pi over 4, well, coterminal angle we could have is going around the circle once, and we'll do this a little bit cleaner, going around the circle once all the way back to that first angle in the third quadrant. If we add, and again, 2 pi to this original angle, or that would be adding equivalent 8 pi over 4, we can consider that next angle as 13 pi over 4. And we can draw one more and consider one more angle that would work for us, and that would be adding 2 pi or 8 pi over 4 to the second angle in purple, the 7 pi over 4. So if we add 8 pi over 4 and 7 pi over 4, that would be 15 pi over 4. So that would be kind of a list of 4 different angles that would work for theta. Now, if I considered going back to this substitution, this is what I started the problem with, and I need to finish with this same substitution, we can rewrite the x solutions as theta divided by 2. And so if I wanted to find x, I just need to take theta divided by 2. And so theta divided by 2 would just be dividing each of those angles that we just found by 2. So that would make these 5 pi over 8, 7 pi over 8, 13 pi over 8, and 15 pi over 8. We'll notice that each of these 4 angles are in the range of 0 to 2 pi. So here we can say that our angle x ranges from 0 to 2 pi. And usually this is where we'll want to be finding our angles. So each of these 4 will be solutions for this problem. So we'll keep with the same approach, finding all solutions within the 0 to 2 pi range for each of these variables. So let's consider, again, working through a double angle with a tangent function. So first, again, I'm going to consider rewriting this angle as a theta. So theta here is going to, again, equal 2x. So I'm looking for the tangent of theta equal to negative square root of 3. So let's just draw in at least the 2 places in our unit circle that occurs. So our tangent function is going to be negative in both the second and the fourth quadrants. And if we consider the places where our tangent is going to be square root of 3, this would be where we have a reference angle, and we'll call it, in this case, a reference angle theta hat at 60 degrees, or we could say pi over 3. So this is where we'd have a reference angle. And you can take a look at our unit circle. You'll find these angles. One coming out here, again with our reference of pi over 3, and another one with our reference of pi over 3 again. So these are the 2 places where my tangent will be negative square root of 3. These specific angles that we've drawn, you'll find on your unit circle. If you take a look, this first angle will end up being 2 pi over 3. And the second angle in the fourth quadrant will be 5 pi over 3. So we have two angles that give us a solution for theta here. So we'll write those down initially. So we'll have theta is equal to 2 pi over 3 and 5 pi over 3. And again, since we have a double angle represented in this theta, we might want to take another round around the unit circle to grab a couple more angles for the value of theta. So again, I'm going to find some coterminal angles. To these given angles, and for this I want to add 2 pi to both of these angles, or we can consider adding 6 pi over 3. That's another way to think about it in this way, since all of our angles here have the denominator of 3. So thinking adding 6 pi over 3 is the same thing as adding 2 pi. So let's add those. So if I add 6 pi over 3 to my first angle, I'll get 6 and 2 give me 8 pi over 3. And then if I add to the 5 pi over 3, we'll get a total of 11 pi over 3. So we have really two sets of solutions now. And so we can now consider my original x variable here. If I rearrange this equation, is going to be again theta divided by 2. And so when I write my list of x solutions, again, this is going to be theta divided by 2. And then we're going to walk through just getting those solutions from our list. So dividing each of the 4 angles by 2, the first angle, 2 pi over 3 becomes pi over 3. 5 pi over 3 becomes 5 pi over 6. 4 pi over 3 becomes, or 8 pi over 3 becomes 4 pi over 3. And then again, dividing by 2 for the last one will be 11 pi over 6. So these 4 angles will give me solutions for the value of x that's in the original equation. All right, we'll take a look at a kind of a little variant off of this with a secant of 3x equals 1. So we'll look at secant of 3x equals 1. One thing that might be helpful here is to rewrite this as a basic trig function. The secant function is the reciprocal of our sine function, so we could rewrite this as the sine of 3x is equal to, well, 1 over 1. Since there's equal to 1, we know that we could just rewrite that as simply just 1. So when we take the reciprocal of 1, it's still 1. So this is an equivalent equation that we can solve to find the value of x. So let's start by taking a look at theta as my value for 3x. That's my substitution. I'll write this as sine of theta is equal to 1. Now let's consider what are the angles that give me the sine of theta equals exactly 1. Well, on our unit circle, my sine is always controlling the y value, or is representing the y value. And so where does our y value become 1 or sine become 1? That's at this top point of 0, 1 on our unit circle. This happens to be at pi over 2. So this angle pi over 2 is the only place where my sine is going to be exactly 1. So if I considered a few angles here, well, the first angle is just pi halves. I can then consider a second angle if I wrap around the circle another time. I'll have this red angle, which would be not just pi over halves, but 5 pi over 2. And since we have a 3 in this substitution, it might be good to get a third angle that goes around the circle a third time. If we wanted to find that angle, we can wrap around our circle one more time. 3 times around would just be another coterminal angle here, which would end up being 9 pi over 2. Graph gets a little messy there, but again, I'm just finding here coterminal angles. To the original pi over 2. So each of those are coterminal. I'm adding 2 pi to each, to the pi halves, and then 2 pi again to the 5 pi halves. So here's some solutions for theta. Pi over 2, 5 pi over 2, and 9 pi over 2. And if I rearrange our substitution, we'll notice that theta divided by 3 is going to be equal to the original x variable. And so each of these values to find x, I just have to divide by 3. So if I divide by 3 on each of these, we have pi over 6. Again, we're just dividing each of these by 3. We have 5 pi over 6. And then the final one would be 3 pi over 2. Divided by 3. So each of these are valid solutions for x. We have 3 of them within the first rotation of our unit circle. Again, we're finding values of x from 0 to 2 pi. So in the second video in this section, we'll take a look at a few more examples with the sum and difference identities. Hope to see you in the second part.